Good morning, student. Welcome to Real Analysis lectures. In this lecture, we will discuss about compactness of a metric space. Okay. So, in R, we might have already known that a subset of R is compact if and only if it is closed and bounded. So, for a general metric space, also we can define what is meant by compactness. So, you take M comma D. This is said to be a compact metric space if it is complete and totally bounded. Okay, complete and totally bounded. Okay, so any metric space which is complete as well as totally bounded is called compact metric space. Okay, now we can see the whatever result we know, uh, namely Henny-Borel theorem for subsets of R. A subset K of R is compact. So K subset of R is compact if and only if it is closed and bounded. Okay, closed and bounded. Right. Proof is not at all difficult. So assume that suppose K is compact. So if K is a compact, then by this definition, it is complete and totally bounded. So compact implies complete and totally bounded. Okay. Now, because it is totally bounded subset of R, we know that totally bounded implies bounded in R. So this implies this is bounded. Now, why it is closed? Why it is closed? Because it is a complete subset of R where R is complete. So we know that it is closed because what are all subsets which are complete? Precisely closed subsets, right? So therefore it is closed and bounded. Conversely, if we take a subset which is closed and bounded, then we want to show that it is actually compact. Okay, but in R we know bounded implies totally bounded, so it is totally bounded. We want to show that it is compact, so for that means we want to show that it is complete. Okay, so to show it is complete, K is closed subset of complete space, right? That means it is complete, right? So what we know, because it is given to be closed subset of R, closed subset of R, right? But we know R is, we know that it is complete, right? That means this is also complete, right? So it is complete and totally bounded implies bounded, so therefore it is closed and bounded, right? Fine. Now you can see simple examples that closed interval 0 comma 1, because it is closed and bounded, it is compact, whereas open interval 0 comma 1 is not compact, right? Because it is not closed. Fine. Now if we see some properties of these compact subsets, you take a discrete metric space. So in a discrete metric space, a subset is compact if and only if it is finite. Okay, so a subset is compact. So take M, suppose this is discrete. Okay, then A is a subset of M, then A is compact if and only it is finite, we want to prove, right? How we can prove that? Suppose assume that A is compact. So suppose assume that this A is compact, that means it is totally bounded and complete, right? So A is in particular totally, we'll write TB just for totally bounded, because we have proved a result. What are all totally bounded subsets in a compact metric space? They are all only finite subsets. So we get that A is finite, right? Conversely, suppose assume that A is finite. Okay, suppose assume A is finite, then we know that in a discrete metric space, if totally bounded sets are finite, so right, using this we get that A is totally bounded. Then why this is complete? Because every subset is closed. So in particular this A is closed subset of M, which is discrete, and we know that every discrete metric space is complete. Okay, that shows that A is complete. Okay, just this property, just like R. Okay, fine. The other property which we can prove is that it is just like a general one. So you can take it. It will be useful whenever we want to show something is compact in terms of sequence. So M comma D is compact if and only if you take every sequence, if and only if every sequence xn, okay, in M, there exists a subsequence xnk that converges to some x in M. So a metric space is said to be compact if and only if every sequence has a convergent subsequence. Okay, fine. How we can prove this? So proof is again not difficult. Suppose assume that your M comma D is compact. Okay, that means it is complete and totally bounded. So it is complete and totally bounded. Okay, then we want to prove that if you take any sequence xn, it has a subsequence xnk which converges. Okay, now take this sequence xn, and using the fact that property of a totally bounded subset, every sequence xn has a subsequence xnk, okay, which is Cauchy. So every sequence has a Cauchy subsequence, right? Now using the fact that it is complete, okay, and every that Cauchy implies convergence. So what we get here is that this is actually convergent. Okay, where we are using what property we are using here, that because this M comma D is complete, so in a complete metric space, Cauchy implies convergent, right? So that shows that M is complete, X and K converges in M. That means every sequence in M has a convergent subsequence. Okay. Now conversely, assume that every sequence in M has a convergent subsequence, and we want to prove that M is compact. Okay, so we know already convergent subsequence means convergence means Cauchy. So what we have got here is that every sequence has a Cauchy subsequence. Okay, Cauchy subsequence, that means that is actually M is totally bounded. This is one of the property we have proved for totally bounded, right? Now to show M is complete, take a sequence Xn. Okay, this is Cauchy sequence. What we want to show, every Cauchy sequence converges, then complete, it will become complete, right? So Xn is Cauchy, right? Then because any sequence has a convergent subsequence, in particular this xn also has a convergent subsequence. Okay, this converges, right? But what we know, if a uh, you have a subsequence of a Cauchy sequence which converges, then the original sequence also converges, right? That shows that every Cauchy sequence converges, that means it is complete, right? Okay, now let's prove some properties of uh, compact subsets metric spaces. If we have from M comma N, this is a continuous map, and K, a subset of M, is compact, then we can prove that f of M is compact. So that means continuous image of a compact space is a subset is compact. Okay. Proof is not at all difficult. What we want to show that f of k. So here we want to write this is f of k actually. Okay. So we want to show that this f of k is compact, right? That means we use the previous this result. A metric space is compact if and only if you take any sequence in that, it should have a convergent subsequence, right? So start with a sequence, say call it yn. Okay, yn is a sequence in f of k. Okay, but how elements look like in any f of k, they are of the form yn is equal to f of xn, where xn is a sequence in k, right? But given that k is compact, right, so and we have a sequence there, this implies there exists a subsequence xnk which converges to, say, call it some x, right? Now f is continuous, this implies f of xnk converges to f of x, right? So but this f of x and k's are nothing but y n. So we started with a sequence yn, then we proved that there exists a subsequence yn k which converges to some point f of x. If you want, you can call it this is y, right? So we proved that y and k converges to y. That means this f of k is compact by previous result. Okay, fine. Now some more results of these properties of compactness is that if take m comma d, which is compact metric space, then any continuous function from that compact domain to R is always bounded, and not only bounded, it actually attains infimum, maximum and minimum. Okay, belongs to F. Okay, F means f of m, whatever you call it. Okay. Proof is not difficult. Again, we can use the fact that since f maps from m comma r is continuous m to r, and m is given to be compact, so therefore by using previous result, continuous image of a compact set is compact, so we are getting that f of m is compact in r. But what are the compact subsets of r? They are closed and bounded, so in particular f of m is bounded, right? That means f is bounded in m. Now we want to show that it attains its maximum as well as minimum, right? Okay, so you can call it n, which is the maximum, that means supremum of f of x, and L, which is infimum of f of x. Okay, we want to show that n comma L actually belongs to f of m, right? I will discuss one, the other one is similar to this. So we want to prove that n belongs to f of m. So suppose assume that n is okay does not belongs to f of m. That means what? So there exists, suppose f of x is not equal to n for every x in m. If f of x is equal to n for some x in m, we are done, right? So we are proving by contradiction. Assume that f of x is not equal to n for every x belongs to m, but n is an upper bound. That means n minus f of x is strictly greater than 0. This is minus, okay, right? This n minus f of x is strictly greater than 0 for every x in m. Now by constructing a new function g of x by 1 upon n minus f of x, we know because f is continuous and this is non-zero greater than 0, so therefore this is continuous on m. Then by first part of this, m is compact, that shows that this g of x is bounded, right? So g of x is bounded means what? There exists some cases that this g of x and mod g of x is not necessary because it's greater than 0 is less than or equal to k, right? Then substitute that and try to bring f of x this side. What we can observe is that f of x is less than or equal to n minus 1 by k for every x in m. That shows that n minus 1 by k, this is an upper bound. Okay, so this is an upper bound and n is the least upper bound. So that means we get that n is less than or equal to n minus 1 by k, but which is strictly contradiction, right? And our contradiction arises because we have assumed that f of x is not equal to n for every x. So at least there is some x such that f of x is equal to n. Same way you can prove it by using this fact that I'll skip. You can show that it also attains minimum, right? Okay. Now we give another characterization in terms of open cover and this one. So M is compact. We will prove that M is compact if and only if every open cover, okay, every open cover of M has finite subcover. Okay, finite subcover. What is meaning of that? That means if G is a collection of open sets in M such that the union covers M, then there are finitely many elements from that G which covers M. Okay, fine. How we can prove this is again not at all difficult one. All follows by definitions and the properties of previous statements. Okay, suppose assume that M is compact, right? Then what we know is that M is totally bounded and complete. M is compact and assume that there is a G collection of open sets such that M is contained in union of such G. Okay, G is open, right? Then we want to show that this M is actually covered by finitely many such GIs. So that we prove by contradiction. Okay, suppose assume that this M is not contained in union of GIs for n for any finitely, this is not possible, right? Okay, then we get somewhere contradiction. Now as M is compact, so therefore it is totally bounded. So M is totally bounded implies M can be covered by finitely many sets of diameter less than 1. So if you want, you can call it this union of AIs, okay, finitely many, some n, some m, whatever, okay, where diameter of each AI is less than 1, okay, AI or ANI, whatever you call it, okay, diameter of each ANI is less than 1. Okay, so M is covered by finitely many sets ANIs of diameter less than 1, but M is not covered by finitely many these GIs. If you combine these two, then what we will get here is that there exists at least one set AI, so you can call it say A1, okay, such that A1 is not covered by finitely many, not covered by finitely many GIs, okay, because if AI is covered by finitely many, if all sets AIs covered by finitely many GIs, then union of AIs is covered by again finitely many GIs, so M is covered by finitely many GIs, which is not true, right? So at least one set is there which is not covered by finitely many GIs, right? That set we are calling it as A1. Now M is totally bounded and A1 is subset of M. Okay, so therefore A1 is also totally bounded and it is non-empty, infinite, that all you can see, because finitely means you can cover it, right? Okay, so A1 is totally bounded, then we can apply whatever we have did for M here, we can do it for A1. That means A1 can be covered by, okay, A1 can be covered by finitely many sets, okay, those sets whose diameter is less than half, right? By again the same argument, this A1 is not covered by finitely many GIs, but A1 is covered by finitely many subsets. Therefore, there exists, you can call it a set A2, okay, which is not covered by finitely many GIs whose diameter of A2 is less than half. Keep on repeating these steps. What you get is at the nth stage, okay, you have A1, then A2, then A3, and so on, okay, whose diameter of AN is less than 1 by n. And at every stage, AN, that no AI is covered by finitely many GIs. So this is important. No AI is covered by finitely many GIs. Okay. Now, what we are going to use is that uh, nested closed sets theorem. That means because A1 contains A2 and so on, so their closures also we have, okay, and diameter of AN is same as diameter of AN bar, which is less than 1 by n, so therefore it tends to 0 as n tending to infinity, right? That means we can apply that you have a decreasing sequence of closed and bounded subsets, therefore closed subsets, therefore you can apply that result, and as diameter tends to 0, that shows that intersection of AN bars, okay, n is from 1 to infinity, this is non-empty. So say suppose x belongs to here, then x belongs to AN bar for every n, right? Now x is also an element of M and M is covered by union, so therefore there exists some G such that x belongs to G and G is open, right? So by definition there exists a ball Bx, some epsilon is completely contained in G, right? Now, because this epsilon is greater than 0, we know that by Archimedean property there exists some natural number such that 1 by n is less than epsilon. That means diameter of an we know is less than 1 by n, which is less than epsilon, right? That means this an, because it is less than epsilon, so an is contained in ball around x of epsilon, right, which is contained in G. This shows that an is contained in G. This is a contradiction because we know that no AI is covered by finitely many G's. In particular, here we are getting AN is covered by one G itself, which is a contradiction, right? Therefore, that contradiction arises by what reason? We have assumed that suppose M is not covered by finitely many GIs, so therefore M has to be covered by finitely many G's. Okay. The converse is easy. We want to show that M is compact. Okay, that means it is totally bounded and complete. Right. Now you can see that if we can create an open cover, then there exists a finite subcover, right? So for a, how we can create a open cover, you simply you take any epsilon, then this x belongs to here. So M is covered by union of these balls, which are open sets. We know that, right? Therefore, This this is a open cover, so therefore there exists a finitely many subcover. Okay, so you can write from I is equal to 1 to n. That shows that this M is totally bounded, right? Now to show that it is complete, instead of taking a sequence, we will take that nested one again, f1, f2, f3. These are non-empty closed subsets of M, such that diameter of fn, okay, tends to 0 as n tending to infinity. Then we want to show that this intersection is intersection of fn's, okay, and this is non-empty. We want to show that, right? But if suppose assume that this intersection is empty, okay, if this intersection is empty, then by taking the complements, what we get here is fi complement is m, okay. That means this m, okay, is covered by these open sets, right? Then using the fact that it has a finite subcover, there exists a finite subcover. That means this M is contained in union of Fi complements. Okay, but again by taking complements, what you get here is intersection of Fi. Okay, but this is a contradiction to this assumption. Okay, intersection of Fi is non-zero for every M, right? So this is a contradiction. That means, well, this has to be non-empty. Okay, if we take as empty, we are getting contradiction, therefore it has to be non-empty, right? Fine. So what we have proved just now is, in terms of open cover, that M is compact if and only if every open cover has a finite subcover, right? We will also give characterization in terms of closed sets. What it says is that if M is compact, then if F is any collection of closed subsets of M such that intersection of Fi's is non-empty for all possible choices of N, okay, then this arbitrary intersection is also non-empty. Okay, arbitrary intersection is also non-empty, and it is not only, it is reverse way also, means it is if and only if statement, right? So M is compact if and only if whenever you have a collection of closed sets such that if you take any finitely many intersection, it should be non-empty. Okay, implies the arbitrary intersection of those closed sets is non-empty. Okay, fine. How we can prove this? Suppose assume that M is compact and F is a collection satisfying intersection of Fi, okay, is non-empty for every possible N, right? Then we want to show that this intersection of F, okay, this is also non-empty. Then we prove a contradiction. Suppose this is empty, okay. Then just like how we proved in previous result, you take the complements, okay, then this will become M. So you have an open cover here, so there exists a finite subcover, right? Okay, which covers M, right? So which covers M, then again take the complement. So what you get here is intersection of Fi's, which is a contradiction, right? So that is not at all a problem. Similarly, to prove converse, that M is compact, the property which we have proved today, we'll take a sequence xn, then we'll show that it has a subsequence which is convergent. Okay, now for this sequence an, you take this an xk k greater than or equal to n. That means a1 is all elements, a2 is from x2 onwards, a3 is from x3 onwards, and so on. Okay, then clearly you can check that a1 contains a2, a2 contains a3, and so on, and each ans are non-empty. Okay, then you take the their closures, then there is, you have a decreasing sequence of closed sets which are non-empty. Therefore what we can assume here is that this intersection of an, okay, or you can call it ai bar, I is equal to 1 to n, this is non-empty because all these sets are non-empty. And what is this one? This is actually the smallest one, which is an bar, so it is non-empty, right? So therefore by assumption, because for every possible n, intersection is non-empty, so therefore this is I is from 1 to n, this is also non-empty, right? So assume again x belongs to here, right? Then this arbitrary intersection of closed sets is closed, so we have a closed set and we have an element, right? So what you can prove that, therefore there exists a sequence xn, okay, which convert of course xnk, okay, xnk, right, which converges to this x, and that is what we want to prove, that there exists a subsequence which converges to this. This implies M is compact. Okay, fine. So these are all some of the results about compactness. Next class we'll discuss about uniform continuity. Okay, and how this compact, complete are related with uniform continuity. Okay, we'll stop here.